Hey, so I'm Jakob, and I work for Klarna as an engineer, and I'm going to talk today about one of the main frameworks that we use in developing our application, and Riak. So Klarna is a payments company from Sweden, founded in 2005. Today we're in all the Nordics, Germany, Austria, and the Netherlands. We have about 700 million users, a couple of $billion in transactions through our system every year. And our entire system is written in Erlang, so we're probably one of the largest Erlang deployments on the planet, about 700,000 lines of code, 80 full-time developers, and been doing it for 7 years, so some experience. From a technical point of view, Klarna is a pretty conventional payment as a service solution. So we have an API, and online stores integrate with us, and then they have a button, buy with Klarna, on the website, and when a user clicks that, we get a call, and then we do various things, and then accept or reject the purchase. So the main differentiator that Klarna has compared to companies like PayPal is that you don't need to sign up for an account, and we take the credit risk for both sides of the transaction. So when we accept the purchase, we guarantee the merchant that he will get paid, and we also guarantee the consumer that he or she won't have to pay unless they're really satisfied with the goods. They have 40 days to pay, during which they can send things back and so on. And so what that means for us is that we have a lot of code that has to do with identifying customers from like a very strict set of information, and risk assessing purchases. So in terms of workload, that means we've compared Web 2.0 sites like Twitter have a very low volume, like tens of purchases per second, and fairly high latency, like 2 seconds for a call. But compared to other payments providers, that's of course pretty good. And our calls are very complex. So for every transaction, we run tens to hundreds of thousands of lines of code to make a decision on how we're going to reply. So our main requirements of our infrastructure are that we must always accept purchases, since we have about 15,000 active online merchants using us, and for many or maybe most of those, we handle the majority of their purchases. So if we're down, many people are unhappy. And we must never, once we've accepted a purchase, we must never lose that data, because we've committed to feeding the credit for that purchase. So if we lose data, it costs us a lot of money. So historically, our system was written in 2005. And it was built on top of Amnesia, and we assume that everyone here is familiar with Amnesia. It's a database that works with Erlang. It's worked so far, but it's clearly not designed to be like the main backend storage system for a web service. And so we've been having more and more problems with it, and we started looking at alternatives in 2011. And I don't have time to go into like the evaluation process. But eventually we ended up with Riak because, and I'm also unfortunately don't have time to explain exactly how Riak works. So if you don't know anything about Riak, you can take a little bit less away from this talk if possible. But the one-slide summary is always writable. You can configure how many replicas of your data you want to have in your Riak cluster. Latency is definitely not sub-millisecond, but it's good enough for us. But unfortunately, it's a key value source. So all your T-set makes are for single objects, not for groups of objects, and it's eventually persistent, so you have to handle write conflicts manually and deal with potentially stale data. So to migrate from this huge system written with on the basis of Amnesia transactions, which are even an Erlang function, and it executes serializable asset transactions, to something like Riak, it's obviously not, requires some major surgery in the system. So we took the opportunity to, since we really had to switch away from Amnesia, and we knew it would take a lot of work, so we decided to take the opportunity to step back and think about how we would like our application to look ideally, and then with that, where we ended. So we really believe in functional programming and its many benefits, but of course when you program a service, you always have this huge thread state in the background in the database. So how do you deal with that? And our answer to this is MeshUp, which I'm going to be talking about today. It's basically a framework for DSL for having business logic that's just pure functions, no side effects whatsoever, and then like an internal running DSL for declaring what data should be read and written, and other side effects as well, but I'm only going to talk about data today. And then we have an engine that orchestrates sort of the calls the pure functions with the correct data, and writes data back at the end of the operation. So I call it a workflow engine because it's also enterprise, but it's perfectly valid to think of it as an interpreter for DSL. So the basic idea is we have this API. It has a number of methods. Each of these methods represents an operation against our system. And they all, I mean, it's like a soft real-time system, so these all follow a pretty straightforward pattern. Like you have a number of major subsystems, and then for each call you will just follow a series of steps, and then you're done, and then you return something to the client. So for us, it typically would be like identify the customer, do a risk assessment, possibly some post-processing for special cases and so on. And now, how do you? I mean, now some of these steps will run code that produces data and other steps, but also some of the data will come from the database. So if we have a returning customer, clearly we need to get that customer's purchase history as part of our risk decision and so on. So how do you make a code that normally you would just do like a database transaction to get data you want? Like how do you make it pure? And we decided that what we would do is, I mean, it's the only way to make it pure, obviously, is to pass all data in arguments and return all data as a return as a function. So we decided to explicitly have what we call a context, which is like, you can think of as the collection of data produced and consumed by the current operation you're executing, or like a subset of the database that the current operation uses, and like explicitly threaded through the steps of the workflow. So concretely, if you MeshUp as a DSL, you write programs in this DSL by implementing some basic interfaces. So for every operation, you implement an interface that describes the overall structure of the operation. And then you implement an interface that does the actual pure computation, and you implement an interface that does the data access. And then the MeshUp engine uses it calls out these interfaces to orchestrate the entire operation and string things together and have data out and so on. And I'm going to go into detail about how all of these work now. So that's the basic approach. So the first interface is the MeshUp endpoint. So for every operation that you want to do in MeshUp, you implement the MeshUp endpoint, and that has one callback function, flow 0, and the flow describes for this operation the series of steps to go through. So the list, and each step is like a tuple of service method. And so the semantics is you say MeshUp run this workflow, and then it goes to the first service and calls the method, and then the next service calls the next method, and so on, and it's done, and then the accumulated data is the result of the entire flow. So this is obviously based on the Erlang MFA notation with the recall that the idea is like you have this workflow, and then you have the data that you thread through the workflow. So the argument is implicit. Every method takes a current data context and returns a new data context, and then you go to the next method with the then current data context and call that method, and it returns a new data and so on. It's like a Unix pipeline. Instead of text lines, you have data context. So that's the overall control flow for operation. To implement the actual things you want to do, you implement the MeshUp service, which has two callbacks, call and describe. So a service can have one or more methods, and each method is sort of made accessible to the MeshUp engine via the call callback. So the call callback takes a method name and a context, and then it extracts the data it needs from the context and calls on every function with traditional Erlang arguments. So this is really just like a calling conventions for a virtual machine or something like that. And then it takes return value and turns it into a context as well and hands it back to the MeshUp engine. So that's pretty straightforward. The more interesting part is the describe callback. So if you recall, the contexts are just data dictionaries. So we say every method takes one argument context, and that context is a dictionary, and then the method has to know what names it wants. It can get it from the context, get the associated value, and then use it to call some function. So to describe callback returns a data structure that describes what the context should look like. So we call this a contract. It has two clauses per method, so an input contract and an output contract, which together the MeshUp engine uses to determine what kind of context to construct to hand to the method at runtime. So context are dictionaries. So a contract just says what should this dictionary look like, which means what key should it have. So it's just a list of names, and the guarantee is that a method will be called with a context having all entries for all these names. And these names can look, so they're completely opaque to MeshUp, but usually use something simple like namespace, list of namespaces and some primary key. And that's if we go back to the workflow. So the semantic so far is, I say I want to execute this workflow, and then the engine will go to the first method, fetch its input contract, make sure that it can construct a context from the current data that it has, call the method from the context, get an output context, check it against the output contract, go to the next method, and so on. And that works fine if method 2 only uses data that method 1 produces. But now to get data from the outside world, which means the database, into this flow, we need to add a store annotation. So each name in a contract can have a list of annotations, and the most important one is the store, which says this name, if it's not currently in the context, you can get it from this store. So a database read in MeshUp corresponds to saying, I have an input contract in my method, and it has a store annotation. And that means if you want to get this data, get it from the store. And the write corresponds to, in an output contract, I have a store annotation, which means the data that I produce here should be written to the store. Yeah, I'm going to skip this one. So stores are just the third interface in addition to endpoints and services, like a fairly straightforward abstraction of a simple database. So it's something that you can read from, write to, delete from, and then it also has some support for changing representation between the database and the application, and a place to put conflict resolution functions for databases like Riak. So specifically, to write a store, you implement the MeshUp store behavior. You implement 6 callback functions. Put, get, delete is the pretty straightforward when it does write, read, delete. Bind return is just so if you program in something like Postgres or Riak, you will store some binding blob in the database. So when you read it out, you want to convert it into an Erlang term, hand that to the application, then you write it back. You want to convert it back into a binding blob and write that to your database. And merge is, so databases like Riak, when you have a write conflict, the database makes it explicit by giving you 2 conflicting values which you have to merge. And the merge function provides a place to put these procedures. So again, the names that you use in service contracts completely opaque to MeshUp. So it just takes them and hands them to some store to read data. So the store implementation will get these in its get input and so on, then interpret it in some way, and that defines what they actually mean. So if I have this as my input contract, MeshUp would go to my store and say get namespace bucket key, and if my store was an interface like an implementation of Riak, it would probably translate it into a primary key read, but it could be anything. So this is completely opaque to MeshUp. It just has this basic notion of I want to call this method, it needs this data, this is where you get it from, and the interface is just read write. Right, so you have these implementations done, you just call MeshUp start an endpoint and with an initial context, and then what it will do is it will say the initial context is the input, and then it will go to the endpoint, get the list of methods that it should execute, go to the first one, get the input contract, check that it can satisfy the input contract, create an input context, call the method, take the result, merge it back into the current context, and so on until it's done with the flow. Then we'll do a commit step on the final context and return the final context to the caller. So that's the base. I mean, it's a very simple. It's just like a level of indirection over instead of reading and writing directly. So normally you would have the method would be a function, and if it needs data, it would read it, and if it needs to write data, it would write it. And so instead of saying this explicitly, you declare what you want to read and what you're going to write, and then you let the engine kind of handle this data structure. And then this level of indirection lets you do a bunch of interesting things that we're going to talk about next. But if there are any questions so far, I think because I'm going to get into some details already next. So it would be good to have the basics are understood if you ask now. It's really very simple. It's just like a lot of, instead of doing things directly, you declare interface and then you do them via one step of indirection. So the key thing here is like instead of having methods that read data directly, I have a pure method and an engine that reads data for me and gives it to the pure method. So depending on how I implement these read and write operations, I get different semantics from my database. So the way we've implemented it currently, that could be changed of course, is that reads are cached in the context and writes are buffered in the context. So if I'm at one of these steps in my workflow, and I have the method that I want to call wants a certain data item, I first check in the context. If it's already there, I take it from there and hand it to the method. If it's not there and it has a store notation, then I read it from the data store, import it into the context, and then hand it to the method. Conversely, if I write, so I have an output, I don't write the database right away. I just write it to the context, and when the entire operation finishes successfully, then only then I write the database in the commit step. So this gives you a certain kind of consistency semantics. And in particular for reads, you have definitely read your writes, because a write corresponds to producing an output, and that's visible in the context right away, regardless of what other flows might be executed currently. And reads are important because you only read from the database the first time, and the second time you read, it's already in the context, so you're going to keep reading the same value. So that makes it a lot easier to. So plain Riak definitely does not give you this, and I mean databases like Riak also don't give you this, like Dynamo-style or anything like that. But by having this sort of snapshot isolation, this sort of like snapshot isolation in the database, and by having that, you can implement these guarantees in user space. For writes, since we commit the entire write set together, we can do it in a way that we guarantee that like all the objects in a write set will be committed on all of them, which you obviously also can do in a key value store. And we can also guarantee that if you write and you get an error, it's not going to show up in the database, which you don't get by default in a Lite-style database. And that's, I'm sorry, I can't go into the background here in 30 minutes. But if you've used Riak, then hopefully you're aware of this, that if Riak tells you a write failed, that doesn't mean that you won't read the value that you just attempted to write unsuccessfully the next time you read a root key. And so how do we do this? So since we kind of redefine our entire write set explicitly in the engine, in the commit step we can do whatever we want with it, and we've implemented one specific strategy that works for us on top of Riak to use these guarantees, and that's we take the entire write set, we use a special Riak bucket as a write ahead log, and then we have on each node in our cluster, we locally track the state of each commit, and then we catch at any point we use the local information to recover using the data ahead log. Specifically, if you're just databases, but if you are in this, specifically we implement something very similar, like this is almost isomorphic to the two-phase commit state machine. So we take the write set, we try to write it to a designated bucket. If that fails, then we apply error to the client and asynchronously loop in recovery in the cleanup step. If it succeeds, we return success to the client and then asynchronously do the rest of the commit, which is take the write set and write the individual keys to the individual buckets. So if you fail it after the log step, you can just retry because you have the entire write set saved. And since if you write the application on Riak, you have to make it to rebase anyway. So you can just take the entire write set again and try writing everything until everything succeeds. and then you commit it, and then you try, you remove the entry from the right-hand log so that it won't get included again, which is just another correct optimization. So, since I'm like a database person, this is of course also pluggable. So this is our implementation, but you can use different kinds of loggers and write log stores in their interface. You can plug in whatever you want to. You could log to Postgres or Zookeeper or whatever. And you can also, there's different commit modes. I've described the default, but you can also, there's one commit mode, write set, which just lets you take any kind of code you want, gives it each write set, and then you can do your own commit strategy on top of it. And we actually use this to run the same application code on top of Riak and on top of Amnesia by just switching out the MeshUp store implementation and the commit strategy. That's how we can kind of migrate incrementally from the old system to the new system with like 90% of the same code, just a couple of strong implementations different. So the other thing that the special interaction provides you is that so you write a program against Riak, and like the traditional issue that people have is that it's hard to think about. Okay, these things that I write will be executed concurrently. They will write into the same key. I will get write conflicts, and then I have to write a function that takes write conflicts and merges them. And so, I mean, this is fundamental to the Dynamo model of the database. So we can't really hide it, but we can make it a little bit easier to use. So what we do in MeshUp is we have some utilities. We have like a behavior of writing resolution functions and various utility procedures, and then like a mechanism where you can say try these different resolution functions in priority order and things like that, and a place to put them in every MeshUp store. You can like specify for each key what resolution function to use. And that's, I mean, you still have to write your resolution functions correctly, but at least it's like a clear way on how to structure this code. The interesting thing though is that you can do preemptive countermeasures in MeshUp. So in MeshUp, a write corresponds to returning a data item in your output context. Right? So MeshUp can track when a data item was read from a database, and then processed by a number of methods, and then eventually written, and then it can check that this update, so it can like preemptively apply the corresponding resolution function to check that if this was like the final update, would it merge with the old value? And that, I mean, to me that's fairly interesting. I mean, so this has been like a mixed success in practice, because I think it's very interesting because it reduces the proof obligation on resolution functions from everything has to merge to if things merge locally, then they have to merge globally. But it's generally confusing to people who haven't used these kind of systems before, so you can enable a second opt-in kind of mechanism. Yeah, so those are two big things. So in addition to having every piece of infrastructure in the interface, so we can transparently run on Amnesia and on Riak and have like some prototype code against Postgres. In the specific case where we run against Riak, the MeshUp direction lets us do custom commit strategies and helps out a little bit with the most like intractable part of a database like Riak, which is that you create write conflicts and you have to resolve them. Which, yeah, it has made it pretty painful for us to migrate from the very strong guarantees of an Amnesia transaction to the very loose guarantees of the Riak value store. So those are really the main things I want to get across. Is, first of all, it's a great idea to really not have any effects in your code, and you're not, I mean, you can write things in Erlang and have your little helper functions to be pure, but if every other function calls a database, it's nothing to do with functional programming, and you get none of the benefits more or less. So it's some overhead to go over an interface direction of everything, but we definitely found it's worth it. And then the second thing is that if you use a more primitive kind of storage substrate like Riak, having a level of direction really lets you kind of add some semantics to it and use it without touching the database code at all. So I just think I have 2 more slides, some miscellaneous features. So things that just fall out from the MeshUp implementation. As you have session handling, you can take a workflow, run it, like half of it suspended to disk, resume on another machine. Yeah, you have like an active shell, you have some simple static checking tools and contracts. There's also a simple promises implementation that we use in 2 cases, I think, to sort of have asynchronous data flow. And of course, the big thing like future plan features are that when you declare all your data dependencies, I mean, it's very easy to write a program that has a data flow analysis and then does some rescheduling and like reads everything in parallel up to a certain point. And it's also very easy, since we don't differentiate between data that's produced by a pure function and data that's read from a database. On the MeshUp library, it's very easy to pre-compute functions and then read data from a cache instead. So really this, taking this step back and which, I mean, it's some work in the beginning, but taking this step and saying, I'm really just going to say I have pure code that has a data dependency, and as long as it gets the data it wants, it can do what it has to do, and then you explicitly declare what data it wants. And like opens up a lot of possibilities and makes things that are normally hard, like having a consistent caching strategy, like very straightforward. Yeah, I'm sorry, I'm open to any questions. Yeah, I've got some supporting code. So in addition, so when you run a MeshUp-based system, in addition to the engine itself, you need usually one package that implements all the interfaces to your storage layer. So we have also called a menu for bringing that on MeshUp. That's like 1,000 lines of code, not much. And of course, we also have a custom Riak client, which hopefully will open source soon. Yeah, conclusions, I mean, I think this is a bit non-standard, and people don't generally think in these terms about their applications. Like, when you get hundreds of thousands of lines of code, and you have like major subsystems that develop with different teams, and all these things run in the same process. I mean, it becomes such an issue to reason about performance. Everyone has queries ad hoc, so getting some structure into it, even though it adds some extra typing, it's really worth it, and it enables a lot of like flexibility and experimenting with different pieces of infrastructure, and extending pieces of infrastructure without actually touching code, just by doing some user templates. Yeah, 2 favorite codes, I agree. And we're going to add. So I think we have 4 minutes for questions.